Our next speaker and the last speaker in this session is Dale Roberts. Dale is a Senior Honorary Research Fellow with CENREM, studying biogeography and speciation in Australia, particularly southwestern Australian frogs, and conservation and restoration biology. Thanks, Dale.
Thanks. What I want to do in this talk is really tell you I have no distribution modelling at all. I don't know how to do a species distribution model. I could probably think about it, but I don't want to. I've got no experiments on temperature tolerance. I've got none of that. Well, a bit like Keith, I've got a history, though, of understanding, I think, how things have evolved and what that might have exposed them to. I also have a background in evolution in biology, so I know a little bit how selection can work and how rapidly selection can work. And so what I want to do in this talk is really give you three things. Oops. I want to get you to walk away from this, I guess, with a bunch of simple messages. First, I want to demonstrate that frogs can evolve very quickly. And I'll do that with some examples of responses of life history evolution to a challenge from chytrid fungus, which is a disease that's killed frogs worldwide. Secondly, I want to show that frogs maybe adapt their life history to climate variation and climate gradients in the wheat belt. Thirdly, I want to look at the age and distribution of frogs across the south coast, which some cases have quite specialised breeding biologies out of whack with the current climate. They're spring and summer breeders, not winter breeders you might expect in a winter rainfall zone. And then lastly, I want to think about whether they can cope with the future, and if they can't, whether we have any real operational ways to deal with the fact that they couldn't. In other words, can we translocate them or captive breed them, whatever it might be. So let's think about, first of all, a very simple example. One of the big threats to frogs globally that's emerged in the 1980s was the appearance of a fungus that's now commonly called chytrid fungus, Batracho, whatever it is, Chytridium dendrobatitis, which has affected frogs globally, affected frogs in Central and South America. It wiped out a lot of frog populations along the east coast in Australia, caused the extinction of a number of species in North Queensland, but only 4 or 5, and it's caused frog declines in a lot of places. It occurs in frogs in southwestern Australia with very little impact. But this is a study on an alpine frog in Victoria, and it occurs in Victoria and southern New South Wales. An alpine species, or high altitude species, or high altitude populations of species, were frequently spots where decline occurred in the 1980s and early 1990s. So these data, first of all, this is a thing that tells you about decline, it tells you about recovery. There are big circles from surveys in the 1970s when Murray Littlejohn was working on acoustics in Latoria Verroe Alpina. There are surveys from the 1990s with little X's, and there are surveys from a little bit later on than that in a little bit later on as well. The picture you see here is of a disappearance. The little X's means things had no frogs, and a lot of these are sites where frogs occurred in the 1970s. In other words, we saw the decline that chytrid fungus can induce. If we come back now and look at surveys in 2011 and 2012, there are still plenty of sites where frogs are extinct. There's these plots over here. But there are a whole series of sites, these little black crosses, where Latoria Verroe Alpina has reappeared. And we don't really know why. But one of the simple explanations is straightforward, that life histories have shifted. If we go back to what happened in the 1970s, we can actually look at the age of frogs in the 1970s because there are a large numbers of frogs were collected. Murray Littlejohn was meticulous about recording a frog, catching it and putting it into a museum collection. And if we look at growth rings in the toe bones of frogs, and you can do that, you can get an annual increment very much like tree rings, then animals back then were living up to 6 years old. They currently reproduce at 2 years old and then they die. Survival rates are 4%. So what's going on? If we look at chytrid fungus, the thing that's killing off frogs, then you find very low frequency of infection in tadpoles, a moderate level of infection but still pretty low in animals that have just metamorphosed, and very high infection rates in adults. And what's happened in this system, or what Ben Shield thinks has happened in this system, is that you've had strong selection against long-term survival. Tadpoles make it, they metamorphose, they leave the pond environment altogether where chytrid fungus is generally picked up, apparently. Apparently because it doesn't seem to quite work like that in Western Australia. They then move away from the pond environment, come back at 2 years old. The first time they come back into the pond is 2 years old to breed. They breed once, they get infected, then they die. So we've had a radical shift in life history in response to strong selection pressure. in this case imposed by a disease which with this particular species is likely to be lethal if you get an infection. There's another example of variation in life history in response to climatic gradients. This is a frog species, Criniosudin signifera. It's about the size of your thumbnail or a bit smaller. Occurs from the far southwest right out to the edge of the wheat belt. Quite commonly breeds in shallow pools, relatively shallow pools that can dry up under dry conditions quite quickly on granite outcrops, but not exclusively. You find it inside the road at Ellicott, for example, on a pond in the corner of the road going north from just right outside Ellicott. So it's a widespread species. It's common and it's abundant. It's been recorded by Burt Main at temperatures up to, I think, like 42 degrees or something, or 38 degrees on granite outcrops, so it's pretty tough from that point of view. Again, we looked at growth rings, and the second thing you can do with growth rings in frog bones is look at patterns of investment. And the spacing of the growth rings is a reflection of investment, in particular in reproductive output, so you get difference between males and females and various other things. We just looked at data from the southwest out to the edge of the wheat belt. We took museum specimens, so they're collected over a long period of time. There's a lot of variability in climate associated with those sort of changes. And then we looked at what happened in terms of life history attributes. And there are two things that come out of this. First of all, if you get out to the edge of the wheat belt, hot, dry conditions as opposed to cool, wet in the southwest, so these are the outer edge of the wheat belt sort of populations, animals live a lot longer. You might not think that's counterintuitive, but if you then look at the pattern of investment, if you live in the southwest, you put all your eggs into one basket, probably breed once at 2 or 3 years old. If you head out in the wheat belt, you're a bit more cautious. You might put a bit in each year because your pond might dry up. There's a risk that you'll actually lose your investment in reproductive output. So across an environmental gradient from 300 millimetres on the edge of the wheat belt to 1,000 millimetres in the southwest, across an incredibly high temperature gradient, probably much bigger than any global circulation model will predict about where we're going with rainfall and temperature, you can adapt your life history to suit the appropriate conditions that you're now exposed to. So those two examples, to me, give us some idea of the potential of amphibians to adapt quickly to environmental change. Do we have particular examples of that? Not necessarily. Let's think of another thing. The second thing I want to think about is climate history a little bit, and history at a variety of scales, because I'm a historical biogeographer. I use molecular clocks to estimate how old things might be. I've done that since the 1980s. And that gives me a quite different view of the scale of process that we might be thinking about. These are data that Craig referred to before. This is the colitrus growth ring history from Lake Tay out towards Esperance somewhere. The little grey plots are the estimated annual rainfall variation based on the spacing of tree rings, which are calibrated against data back to about 1900. We know that climates in southwestern Australia, these are rainfall anomalies back to 1900, go up and down. It's been dry, it was relatively wet. Back here when I came to Western Australia, I thought it was wet, but apparently it was dry. So things are not all quite as obvious as they seem. But what you can see here is, yes, there's between-year variation and there are long-term cycles. So there's a process, if we think about what I talked about with life history adaptation, where things might have moved around historically already. They might have changed direction in terms of where they're going. If we go a bit, we also have interposed on that, and the reason I asked my question about cyclones and big rainfall events is occasional major rainfall events. These are data from the breaking of the millennium drought from the affected frogs in Eastern Australia. In Eastern Australia, for example, the green and golden bell frog from occurs in New South Wales and Eastern Victoria, there were major recruitment events in the Brokehaven River catchment after major rainfall events. Thousands and thousands and thousands and thousands of frogs across the landscape, which have slowly contracted back in the last few years to a more, to their pre-major rainfall event distributions. I worked on the River Murray in South Australia in 73 and 74 when you had similar rainfall events. The Murray and the Darling flooded together in 74. Frog distributions were moved around by major rainfall events. So these periods of very high rainfall, one of the reasons I asked about intense rainfall events, was maybe periods of very important recruitment and redistribution of some amphibian species in the landscape. So we don't need to be afraid of the fact that some of these things might change in the future. What I'll look at now is a few species that occur across the south coast. This is the sunset frog, Spicospina, was found in 1994, formally described in 1997, or found by white people in 94, who knows about it before that, quite possibly was well known. And it's a spring into summer breeder. If you look at a large majority of the frogs in the southwest of Western Australia, 30-odd species, the majority of them are taking advantage of either autumn rainfall or winter rainfall for breeding. A number of species lay their eggs out of water before the autumn, when it starts to rain in autumn, and are dependent on winter rainfall for flooding and then tadpole development. There are also a bunch of species that do things differently. So Spicaspina breeds in the spring, November, December, that sort of time of the year. It lives in peat swamps high in the landscape. It's not dependent on winter rainfall supply of water, so whatever water is seeping into those peat swamps is a critical resource. It breeds intensively after fire events because that raises the water table and builds up little pools in the landscape. And it's got a range from on the Bow River and Upper Kent River drainages. What do we know about it? It's been out there for about 26 million years. It's persistent. It's related to Euparlea species in eastern Australia, which are widespread and broadly distributed along the east coast and across northern Australia. They're all spring-summer breeders. It's retained what you would guess is its ancestral breeding biology and breeding season, despite the changes that have gone on in climate around it. And if we look at historical, and we can see the same thing in Geochronia, the Geochronia rosea complex, there are 4 species, Alba, Vitellina on the threatened species list, Rosea and Lutea are widespread. 40 million years split between them, 8 million years split between these two. Again, they're spring into summer breeders with direct developing eggs, no free-swimming tadpole stage. They require moist soils in the spring. So we've got these examples of apparently historically conserved breeding systems that have persisted in southwestern Australia despite an extensive history of climate change. Go back to the Miocene, 23 million years ago, and as Keith pointed out, we had things like rainforests and wet sclerophyll forests all over southwestern Australia. If we follow that through, the Miocene slowly dries out. You run into the Pliocene 5 million years ago, you get rapid oscillations between wet and dry conditions. You come into the Pleistocene and 3 ice ages where you had reduced rainfall but lower temperatures. So these things have persisted through an extreme level of variability in climate, and that leads me to conclude that we have a real option here that frogs perhaps can cope with remarkable variation in climate without a major disaster happening. The alternative is that we might think about the possibility of manipulation of ranges. And for example, with Geochronia vitellina, the orange-bellied frog, that's been attempted. So far, it is remarkably unsuccessful. Why? Almost certainly the characteristics of the swamps that they occur in aren't being met in the sites they're being translocated into. And that will be, particularly for these restricted species on the south coast, an ongoing major problem. If we think about translocation as an option for most fauna in the country, and if you look at the history of the effectiveness of translocation, for mammals as a very good example, except when you put a fence around and you kill off the foxes and cats, the success rates are remarkably low. So I think we need to think quite critically about what we can do, or whether we may perhaps have to accept and go with the flow and live with the outcomes. And I think for me, for amphibians, that's probably where we sit. Thank you.